This is the prediction of the so-called saying that size matters, also known empirically in economics, economies of scale. In this lecture, I anticipate that, meaning I predict that, even though I'm not an economist, you see. It's much more exciting to discover something when you're not looking for it. Yeah. It's a lot more exciting than going fishing. There you go, look for a fish, come home empty-handed. That's the opposite of what I just spelled out, which is called serendipity. Which is the mental, let's call it happiness, of discovering that for which you're not looking, you see. The word serendipity for the road to unintended discovery. So here's the simplest drawing of a heat engine. There is a heat transfer rate coming from a high temperature called TH. There is a heat rejection rate at the other end. And the all-important power output. And because makers of these machines were, like today, mortals, the machine was not ideal. It was operating irreversibly in cycles. And in the last lecture, I painted here the simplest model of the same heat engine, a model that accounts for irreversibilities, namely two temperature gaps between TH and THC, where capital C comes from Carnot, and then between TLC and TL, Carnot, because in the so-called temperature gap between these inner temperatures, there are no irreversibilities. So ideality is the meat in the sandwich. The slices of bread are these two temperature gaps that are necessary for forcing the heat transfer rates to traverse the gaps. You see? So that's the move I make in my own mind, because I'm really interested in the relationship between physical structure and irreversibility. The structure in this case is the fact that I have a sandwich. Previously, I had nothing except hand waving. The report that the efficiency here is smaller than the Carnot efficiency. Here I'm beginning to show why the efficiency is smaller. Here is the same W dot, by the way. And I start putting important equations on the blackboard. So this W dot is obviously the heat input, Q dot H, times the local Carnot efficiency, which is 1 minus TLC over THC. There are more such, let's call them modeling moves. The next two come from the subject of convective heat transfer, and they have to do with the physics of heat transfer, which is that there is no temperature difference, there is no thermal diffusion or a flow of heat from hot to cold. All right, those are facts, and those facts are presented by these two proportionalities. So here are two more. I referred to let's say real life, that which means money, which means that you have to pay for these things. So the heat transfer surface that's traversed by the upper heat current, I call it A sub H. There's another one here called A sub L. And then the sum of the two is proportional to the means or money supply of the builder. And this capital A is fixed because life is not fair, you see. If you know some of these maxims, let me know because I collect them. But to use this piece of reality in conjunction with the system, I recognize what I mean by conductance. Conductance is the product of the heat transfer area and a heat transfer coefficient called, I put a bar on top to not to confuse it with the specific enthalpy. And to figure out how to predict heat transfer coefficient, you have to go back to your undergraduate course on heat transfer or take this other course next fall. But in any case, this factor is no mystery. And the same with the other conductance, which has its own heat transfer coefficient. And then I made the assumption that these square boxes are, if not equal, they are comparable as order of magnitude, which means that the so-called size constraint becomes a conductance constraint. I slip into the discussion 1 degree of freedom. So the lone degree of freedom is my freedom of allocating the fixed inventory of capital C or capital A, allocating it or dividing it unequally or equally between the two ends of the model. In other words, big heater, small cooler, or small heater, big cooler. And so the lone degree of freedom is called X, defined as the fraction represented by the hot relative to the total. And that means that 1 minus X is CL over the total. So these are just the definitions of the degree of freedom, which is called X. I repeat the F word, which is freedom. Without freedom, there is none of this thing you hear all over the place, including this campus optimization, organization, intelligence, whatever they call it, you know. Without the physical facts that allow you to make change, there is none of that. And that piece of physics is called freedom, or if you want, degrees of freedom. The part I skip, because it is in fact a very, very nice exercise, is to use the system of equations for the purpose of eliminating most of the unknowns from one equation to the next. There are lots of unknowns here. These temperatures, inner temperatures, THC, TLC, they vary with the degree of freedom. So does W. So does the heat rejection rate, this QL. You eliminate them, and then you, through that exercise, you evaluate the actual efficiency of the irreversible engine model, namely W dot divided by Q dot H. So this is the object of the analysis. And if you do the analysis correctly, you arrive at the following formula. That the efficiency equals 1 minus, it better be 1 minus something. And then in the numerator is what one would expect from the Carnot efficiency. But in the denominator, a brand new expression that has to do with, first, the heat input, because efficiency is a dimensionless value on a per unit of heat input that comes from the top. So Q dot H divided by the fixed high temperature and the total inventory of conductance. And then in here, a factor, a binomial expression that depends on the degree of freedom. In other words, the efficiency depends on the degree of freedom. And the dependence is accounted for by a function called f of x. F obviously takes values between 0 and 1. Because 0 means nothing at the hot end, and 1 means nothing at the cold end. You see? And in other words, in both places, 0 and 1, this function blows up, clearly. But the first term, 1 over x, goes from huge to the value 1. The second term, this is what a binom is the sum of two terms. The second term is the mirror image of the first. You get the second term by replacing x with 1 minus x. And that means that so that's the first term. The second term is that. And the sum of the two is this bucket shape called f, which, because of symmetry, reaches its minimum at, you can figure out, 4. And that happens at 1/2. Meaning the equipartition of hardware inventory between the hot end and the cold end is the design in which this factor is the smallest, meaning the one in the round brackets. So we figured out that there is a so-called F minimum, which I will be using in place of this factor very soon. Let me write the minimum here. And then, do you see how fast I'm doing my calculus? I'm not even doing calculus. I'm making a drawing. Last night I ran into one of the many quotes or dictums from Napoleon, you know, the first one, Bonaparte. And he said, obviously he was talking to his generals, a good sketch is much better than a long speech, you see. But the kind of sketch we're coming up with here, you don't even have to make it, because this sort of thing is in the mind if you look at this expression. If I was clever enough to find the minimum of this expression, that is the same as saying that I found the maximum of the denominator. And to find the maximum denominator is the same as celebrating the fact that you found the minimum of this negative term. And that is also the same as trumpeting the discovery of the maximum efficiency. So the punchline is that the maximum efficiency, which I will write over here, is indeed equal to 1 minus this thing on top, TL divided by TH. And downstairs, something shorter. I hope I wrote something that's easy to see over here. And if you look at this expression, degree of freedom represents your freedom of choosing those sizes relative to one another. Big here, small here, or small here and big here. And you just discover through this very, very crude model that a balance between the two is advisable. Balance means, if not exactly equal, as this 1/2 would represent, but certainly comparable, then that is the secret to keep in mind, that there's a balance to be discovered between the two ends of one of those heat engines. The message here is that to have an even greater maximum efficiency, meaning even greater, you have to contemplate, you have to reach deeper into your pocket to buy a bigger machine. So you discover that size matters. So greater size. Through greater size, you achieve a greater efficiency. Therefore, economies of scale, this is the observation in economics and also in business. You want to transport something cheaply, you put it on a big truck along with thousands of like objects. So, and this is called economies of scale. Today in this lecture, discovered, not observed, you see, or predicted if you want. In my own work, this was an example of serendipity, because I told you, I didn't tell you. Where I come from, they're not teaching economics. Under communism, they were teaching something called Marxism, which was the equivalent of not teaching economics, because in a so-called socialist society, private property was illegal. So what economics is that? By that I mean the private ownership of means of production was illegal. So yes, an unintended discovery. An important one.